Okay, we haven't talked about complex numbers yet. What is a complex number? A complex number is a mixture of a real number. Again, when you think of real numbers, think of the number line that you're used to graphing a single number on. You can locate any point on the number line, fraction, whole number, the opposite of any whole numbers, decimals. Well, a complex number is a combination of a real number and an imaginary number. So any number of the form a plus bi, where a and b are reals, a and b are, a and b are real numbers. Any number that looks like this, a plus bi, any number of this form is called a complex number. So let me give you some examples. 2 plus 3i. We think of that as one object, one quantity. That is a complex number. Okay? 2 plus 3i. What's a? 2. What's b? A lot of books would call a the real part and b the imaginary part. And it differs from book to book. Some books call b times I the imaginary part. Some books just call the number in front of the I the imaginary part. I believe, if I remember right, your book would just call the 3 in this case the imaginary part. But you need to just be able to identify them as A and B, and that's good enough. How about same thing, same idea. What if we had 3.1 minus pi times I? Pi, the usual 3.14159, blah, blah, blah. That's a complex number. What is A? 3.1. What is B? Well, you'd have to include the negative, right? Just like you do with coefficients and polynomials. So negative pi. Don't round off, just negative pi. What if I gave you the number 10? First of all, is the number 10 a complex number? So the real question then is a real number a complex number? Well, what if I did this? 10 plus 0, well, wait, let me put an equal sign. 10 plus 0 times I. And, I mean, we're going to have to assume that 0 times I is 0, just like any other multiplication, but we'll just say, hey, that's true, and say that's a definition, and don't worry about it. Then is it true? Yeah, 10 is a real number, but it's also a complex number. So A in this case is what? 10, and B is 0. So true, this would be an excellent question on the next test. True or false, every real number is a complex number. So think of a real number like just in generically A. True or false, A, it's a real number, but is it also a complex number? Yeah, it's true, because couldn't I do that trick I just did with the 10, with the A plus 0i? Couldn't I write A as being equal to A plus 0i? Yeah. Every real number is complex. Does it work the other way around? Every complex number is a real number? No. The first two examples of complex numbers would not be real numbers. So 2 plus 3i, no. It has one, think of it this way. It has one foot in the real numbers, the number 2. It has another foot in the imaginary numbers, 3i. So that would be false. That would be false. So that means the set of complex numbers contains the real numbers. Remember what the real goal was today. The real goal was to add, subtract, multiply, and divide complex numbers. But you know what? Once you understand what complex numbers are and what I is, the 4 operations are no big deal, because we perform them the way you think we would. So let's start with addition. Compute. In part A, let's take the complex number 4 minus 3i, and add it to the complex number negative 2 minus 5i. If you were inventing addition of complex numbers, which somebody did just a couple hundred years ago, really, how would you want to add these together? You would want to add probably the real part and the imaginary parts. Just like terms, thinking of them as like terms, right? Thinking of the real part as like terms, constants, and the imaginary part as like terms. Even though don't think of I like x, though, because I is an actual specific number, whereas x represents usually a variable. Okay, so if you do that, what do you get? 4 plus a negative 2, 2, negative 3i minus 5i, minus 8i. Is it really that easy? Yes, it's really that easy. I feel like I'm selling you a food processor for only $19.99. Complex numbers, it grinds up, adds them together. 2 minus 8i. So that's about, I mean, isn't that about how you'd want it to work if you were inventing the addition? Yeah. What else are you going to do? Well, is subtraction going to be much different? So in part B, we're taking negative 2 plus 4i minus the entire complex number, negative 5 plus 7i. So we need parentheses around it because we're thinking of negative 5 plus 7i as one number. In the last example, the parentheses weren't necessary. In this example, the second set around the negative 5 plus 7i, they are necessary because what do you think you have to remember to do? Distribution property, yeah. So I can just drop the front set of parentheses, negative 2 plus 4i, but then distribute them minus, what do you get? Plus 5 minus 7i. You've turned it into an addition problem, right? Essentially, and when you subtract 7i, it's adding a negative 7i, right? So add the real parts, what do you get? Negative 2 plus 5, 3. Add the imaginary parts, 4i plus a negative 7i, or just 4 minus 7i? Minus 3i, yep. So 3 minus 3i? Yep. It's really not new, is it? The symbolism isn't new, and how we work with the symbolism. The numbers are new ideas, but the actual way we treat them isn't. Yeah?
So you wouldn't go any further than that?
You can't. You can't go any further than that. There's nothing else to do. It would be like adding. You can't add or subtract unlike terms, right? So there's nothing else to do.